Hi everyone, and in this video today we are going to learn how we can use the residue theorem, or so to say residue calculus, to evaluate different kind of improper integrals. So what are improper integrals? If you recall from your calculus courses, that an improper integral will generally have a following form. That is, the limits either start from minus infinity to plus infinity, or it can start from 0 to infinity. So these are the kind of things that we are going to consider while evaluating improper integrals, and we'll see how the complex calculus, or let's say complex analysis, helps us in evaluating them. In fact, it's a very powerful tool to do this kind of integrations. So first, let me give you some information that we consider functions of the form like this, px and qx. So this is a rational function, and we require that they have real coefficients, and we also require that they have no factor in common. So this p by q is a rational. This whole thing, it's a rational function. So this means the coefficients of these functions are real. So the coefficients, let's just say, belongs to R. Now you might ask, where is this coefficient thing coming from? Well, if you recall from your calculus course, that a function can be written in a power series format, and the power series will have some coefficients, and those coefficients will be real. That's what I mean by the coefficients belongs to the real number. And we also require that they have no factor in common, just like rational numbers. So now if you consider an integral to a function like this, let's say you are considering an integral like this, most of the time real variable calculus makes it hard for us to evaluate this kind of integrals, but using the complex variable notation we can actually do it using contour integrals. So what happens is that first, so let me just draw a boundary. At first we promote the x variable to z variable, and this is an important step. That is, we are going from real plane to the complex plane. So all the x's will now be replaced with z. That means some complex variable. And then what you're going to do is that instead of writing minus infinity to plus infinity f of x dx, this will be replaced by a contour integral f of z dz. Now up to this point everything looks fine. However, you can ask, okay, since I'm considering a minus infinity to plus infinity integral, what should be my contour? So let's try to give you an idea what should be our contour. So imagine this is the complex plane, and let's say this is a point, let's call it minus r. This is a point called plus r. And if you recall that this is just the real part, that is the x-axis, and this is the imaginary axis, or so to say the y-axis. And let's say you start from here, this minus r. You go to this plus r like this, and then you take a semicircular path back to this point again. This is one way to think of it. And if you see from the graph, this semicircle actually has a radius of r, right? And we are calling this semicircular path over here, we denote it as CR. That means a semicircle with radius r. And if you recall from calculus that this minus infinity plus infinity thing is actually coming from limit, let's say there is some r value, this goes to infinity, this tells me that this r goes to infinity thing will actually give me this. That means you evaluate this integral and then you take r goes to infinity, and that should give you this minus infinity to plus infinity thing. This was the definition of the improper integral. So from this definition over here we got to this contour. That means you start from some minus r, you go to r, you take a semicircular path, and finally you make this r goes to infinity. However, this is one of the cases, and this case is only valid if f of z is analytic on the upper half plane except for a finite number of points. So let me elaborate on that. What do I mean? So now forget about this f of x dx, that is a real valued integral. Rather, imagine this imagine another integral that is defined on this contour. So this means f of z dz, and there are two contours. You can decompose them in two ways. One is over here and two is over here. So on the first line the z will have a form of x plus iy, right? But y here is 0, so z is equals to x. So that's why you can write it as from minus r to r f of x dx. And the second one can be written simply as this. Obviously the second contour, that is the semicircle, it can be parameterized like this, capital R e to the power I theta, but we are not writing it explicitly over here. So there are actually two parts when you promote your real integral to the complex integral, and this is the main punchline. And we are saying that if we consider f of z is analytic on the upper half plane except for a finite number of points, and none of the points that we are considering lie on the real axis. That means your f of z is analytic through all the upper half plane except for some points, and let me mark those points. Let's say these are the points. So these points are the singularities or the poles. So these points are singularities, right? And this, if you already know from your Cauchy's integral theorem that if your function is analytic through and on the contour, then the net closed contour integral would be 0. However, if you have some singularities, you might get some obviously you will get some non-zero contributions. So that's why this idea is coming from. That's let's say it's just an extension of this thing, the Cauchy's theorem. So also we require that none of these singularities lie on the real axis. And what happens when the singularities or the poles lie on the real axis is something we're going to consider in the future videos. So this will be the main principle through which we will conduct the evaluation of improper integral. And if you see or notice that if you take the limit r goes to infinity, this part is just reducing down to the integral that we wanted to consider. However, there is this c over an extra piece, and for today's video we are going to assume that this part will be 0. However, this is not always the case, so this is only for today, or let's say for today's example, and in the next video we are going to justify it, that how it actually goes to 0. So this assumption is only valid for today, for this lecture. So let us try to see an example, and that will clear things up. So let's call this example 1. It will be a pretty simple example, and we are considering an integral like this, from minus infinity to plus infinity dx x squared plus 1. You already know that I can do it with the tan inverse thing, but let's try to do it from the contour integral point of view. So firstly, you can notice that f of x is just 1 by x squared plus 1. So now what I'm going to do is that I'm going to promote this guy into a complex variable function. Then I'm going to write a counter integration. So now we promote these stuffs to complex plane. So our f of z will be 1 upon z squared plus 1, and we define a contour integral like this, and our contour will look something like this, from minus r to r, and this is the semicircle, and obviously these are your axes. So if you recall from Cauchy's residue theorem that you have this closed contour and you have some points, let's say poles or singularities. So this integral around this closed contour, obviously we are going on anti-clockwise direction, and if you circle this contour once, that is, if you consider a closed contour integral, this is just equals to 2 pi I and sum over the residues, right? So this is the thing that we're going to use, Cauchy's integral formula, or let's say Cauchy's residue theorem, or whatever you want to call it. So at first we are going to write down the decomposition on the contour f of z dz. It's from minus r to r, and since this is on the real axis, this is just f of x dx, right? And there is this semicircle guy, f of z dz. And again, we are considering that for today, when this r goes to infinity, because we are considering and minus infinity to plus infinity integral, so obviously you need to take the limit r goes to infinity, and we will assume when limit r goes to infinity, this integral, that is the extra piece that we're getting from here, this is the extra piece, this will be 0. Again, this is not always true. And the justification will be on the next video. Okay, so let us work with what we have right now. So since we are taking this to be 0, this will just be 0. And finally we can take the limit on this side, and if you do that, so again let me just write it down, f of z dz, limit r goes to infinity, r minus r, f of x dx, right? And this is just minus infinity to plus infinity, f of x dx. Okay, but where is the result, right? If you recall Cauchy's theorem that I wrote over here, you can see that this line will actually give me the 2 pi I times sum over the residues. So let me write it properly. So this 2 pi I times the sum over the residues will actually be equal to the minus infinity to plus infinity f of x dx. Alright, so let's try to calculate the residues. So our function was z squared plus 1. So if you write it like this, z plus I and z minus I, because z squared plus 1 equals to 0 will give you this z plus I and z minus I thing. And since you are enclosing the contour on the upper half plane, you will only have z equals to I. So let me draw the contour again and write this whole thing again for your convenience. So this is just 1 plus z squared. So this is z plus I, z minus I, and if you draw the complex plane, you draw the contour. Oops, it doesn't look like a semicircle, but whatever. So one of them is over here, one of the singularities I, and another one is over here minus I. So we are only considering the upper half plane because we are enclosing the semicircle on the upper half plane. And if you recall how to calculate residues, you will remember that the residue at point I, since we are calculating for point I, this will be just limit z goes to I. Since it's a pole of, or a singularity of order 1, so there will be just 1 divided by 1 minus 1 factorial, that means 0 factorial, which is just 1, and there will be d 1 minus 1, d of z 1 minus 1. Our function was z plus I, 1 upon z plus I times z minus I, and since we are considering the residue at point I, so in the nominator, that is on the above, we will have a z minus I thing, right? And these two will cancel each other out, and this weird thing that I wrote over here is just d of 0, dz of 0. This means no derivatives, so you don't have to differentiate this thing, right? And 0 factorial is just 1, so you take limit z goes to I, 1 upon 0 factorial, that is just 1, because 0 factorial itself is 1. This is just d to the power 0 by dz0 is just saying that no derivatives are involved here. So you will have a limit z goes to I of z plus I, right? And if you evaluate the limit, this is pretty simple, only 2I. Now we have found the residue. Since we there is only one pole inside this contour, so in the summation of the residues there will be only this guy contributing. So we'll have our 2 pi I sum over the residues as 2 pi I times 1 upon 2I, and you can see this is just pi, right? Pretty simple result. And if you recall, this 2 pi I residue was equals to minus infinity to plus infinity f of x dx, that is the integration of f of x from minus infinity to plus infinity. So finally, from minus infinity to plus infinity, f of x dx is equals to pi. That's it, because our f of x was what? 1 plus x square, right? From minus infinity to plus infinity, and this is just pi. Yeah, and you can easily verify it with the tan inverse formula as well. So the subtle thing about this semicircle is that in this video we have considered that it when r goes to 0, that means the radius is very large. This extra piece that is coming from this semicircle will go to 0, this extra piece over here. However, there is a justification for that, and we will see this in the next video. And thank you.